Hey everybody, and welcome to what is either a very long video or a very short course on using window functions in SQL. Now, window functions are absolutely one of the most powerful techniques for analyzing data in SQL, and from my experience, they're also very prominently featured in many data analyst interviews. As such, if working with data is going to be a big part of your career, window functions are one of the most important things you can learn. Now, for context, this long video / mini course is actually taken from a section of a very long course of mine on advanced SQL techniques for data analysis. So you'll probably want to have at least some background in SQL to get the most out of this video. For example, select, from, where, aggregate queries, and so on. Now, this video also makes use of a popular example database for SQL Server called AdventureWorks for all examples. But don't worry if you don't have that installed or are using some other version of SQL besides SQL Server. Nowadays, window functions tend to work pretty much the same across most popular relational databases. So you should be able to apply what you learn here to whatever database you happen to be working with. Okay, so I think I've gotten all the caveats and disclaimers out of the way, so let's go ahead and jump right into the actual SQL stuff.
Assuming you've worked with aggregate queries in SQL, you know how useful they can be in performing calculations like sum, count, or max, just for example, across the rows of our data, while optionally grouping the results of these calculations by other values in the data. However, these functions also force us to compromise the level of detail available to us in our query output. For example, if you want to see a count of all the rows in your table, not broken up into groups, you won't actually be able to see these rows. Instead, your output will simply consist of the count and nothing else. So if we look at the records from our sales order header table, and then contrast that with a query that takes the sum of the total due column from that same table, you'll see that we lose all the detail. We lose all the columns and all the rows in that table. Everything is boiled down to this one single number. And then if you want to add new fields, you'll have to group by them, meaning the grand total will now be divided up across multiple groups based on the values in the fields you added. So we can look at this query here. So now we've added salesperson ID, which is fine, but if we're really trying to get to the total amount of sales, we're not seeing that in any one of these rows because that total amount is being broken up by salesperson ID. And then if we added another field to group by, it would be broken up even further. Now, this may be fine in many cases, but what if you need to see aggregate totals, like dollar totals or row counts, alongside the individual rows of your data? For example, let's say you wanted to compare an individual salesperson's year-to-date sales to the total of all year-to-date sales in our table. Traditional aggregate functions won't be able to help us here. Well, that's where window functions come in. Like aggregate functions, window functions allow you to perform calculations like sum and count across groups of rows within your data, or alternately, all the rows in your data set. Whereas aggregate functions collapse the rows of your data into groups based on the unique values in the columns you include in your select statement. So you can see that the two records for Brandon in our detailed data example here have collapsed down into one single record where those two sales amounts have been added up to one number. Now, by contrast, window functions allow you to retain row-level detail while performing the same types of calculations. The aggregate calculation simply becomes another column in your query output. Now again, you see that we've got two records for Brandon here in our detailed data, one with a $100 sales amount, one with a $200 sales amount. But in our window function version, we have this new column, total sales, where both records for Brandon reflect that total sales amount for Brandon. So we get the same result that we got with the aggregate query in terms of calculating Brandon's total sales, but we don't have to collapse our data down based on including that aggregate calculation. We can just tack it on as a new column in our query output. Now that we know when we might want to use a window function, let's take a quick look at the syntax before we dive into an example. Now the first piece is just a function. It could be sum, count, max, or any other aggregate function, or one of a number of ranking functions specifically used alongside window functions, which we'll dig into a lot more later. But for now, we'll just stick with aggregate functions and sum in this example. Now the second piece of the syntax is what makes this a window function, the over keyword. Now when no arguments are passed to over, as in this case, it simply applies our sum function here across the entire dataset, returning the result for each record in the dataset. Now arguments can also be passed to over, as you might have guessed because of the parentheses after it, and rest assured we'll get into that a lot more later. But for now, let's take a look at how a window function can help us with our year-to-date sales example. So here we have commented out a total year-to-date sales column. So let's go ahead and code this up really quick with a window function. So what we'll want to do is first type a sum, because window functions will start with some kind of just a function that you're applying across your whole data set or groups within your data set. And we'll plug sales year to date into that. And then we'll simply add over with parentheses after it. Now let's try running that. And you'll see that we get the same number for each record in our data set. And that number reflects the total year-to-date sales across all salespeople. And just to confirm that, let's run an aggregate query that just pulls that. And you'll see it's the same number. So as you can see, we were able to perform this aggregate calculation and include it in our query output without otherwise modifying our query in any way. We have all these other columns. And if you wanted to add a new column, like let's say we want to tack on sales last year, we can do that. No problem. Unlike an aggregate query where now you have to include that new field in your group by, and it adds one more layer of grouping that breaks your number that you're summing or doing a max of or averaging out over more and more groups. Here, you can keep that sum calculation over the entire data set, no matter how many columns you choose to add. And we can just as easily add more columns with new and different aggregate calculations, again, without impacting the rest of our query output in any way. For example, we can also add the maximum individual year-to-date sales amount for any salesperson as another data point to compare to our individual sales numbers. So this is going to work almost exactly like the total year-to-date sales, so much so that we're just going to copy the code. The only difference is we'll just type a max. And let's see how that works. So now what you see for each row is the maximum sales year to date for any of our salespeople. And again, just to confirm that this is working, let's pull that as an aggregate query. And it's the same number. Now, even better, we can actually use these aggregate totals in row-level formulas and calculations. If, for instance, we wanted to compute each salesperson's year-to-date sales as a percentage of the highest performer's sales, which is the number we're looking at right here, window functions make it really easy. So to do that, all we have to do is divide our sales year-to-date field, which is a row-level field that's specific to each salesperson, and we divide that by our window function here that calculates the max sales year-to-date over all of our salespeople. So what we should get is any given salesperson's percentage of the very best salesperson's performance. And what we should also see is whoever got the best performance should have a 1 in this column because their sales are 100% of the best salesperson sales. All right, so if we scroll down here, we see it looks like it's working as it should. We see one record where the percentage of best performer is 100%, and this is in fact the person who had the best sales year to date. So this is just an example of how you can code a pretty useful metric, one that lets you compare an individual salesperson's performance against some kind of benchmark pretty easily using window functions. In short, window functions give you the power to include aggregate calculations in your queries without changing the rest of your query output in any way. The calculation is simply added to your dataset as another column, with no impact on the rest of the data. But you may be asking, since window functions can perform aggregate calculations on the rows of our data, similar to aggregate functions, is there a way to break these calculations out based on groups within our data, like we accomplished previously with group by? There sure is. It's partition, and we'll look at how to plug it into our window functions in the next video. I'll see you then. Welcome back. We've seen how to perform aggregate calculations across our entire dataset without losing row-level visibility into our data using over. But what if we wanted to roll those aggregate totals up into groups the same way we do with group by using aggregate functions? How would that work with over? The answer is partition by. When we combine our over function with partition by, we now have the power to compute aggregate totals for groups within our data while still retaining that row-level detail that distinguishes window functions from aggregate functions. The first step partition by takes is to assign each row of your query output to a group, but it does this behind the scenes without collapsing your data into fewer rows as with group by. So how does it do this? Kind of like group by, but not exactly. Instead of groups being assigned based on the distinct values of all the non-aggregated columns of our data, we have to specify the columns these groups will be based on. Let's dive into some code to see what this looks like in action. First, we'll try grouping our sales order detailed data by product ID and order quantity using a traditional aggregate query. As you recall, this operation works by creating a group for each unique combination of values from all the fields listed in our group by, product ID and order quantity in our case. The aggregate calculation or calculations of our choosing, sum, count, etc., will then be performed over each of these groups. So how does this kind of grouping translate to our window functions? Here we have another query against the sales order detail data, this time with an over function that calculates the sum of line totals for the entire dataset and returns this value to each row. So let's run this really quick and see what the output looks like. Should be fairly familiar to us by now. Now, if we want this sum broken out into subtotals, similar to our aggregate query above, we will still need to spell out the columns that define our groupings, product ID and order quantity. And that is done in the partition by clause of the over function. So here's what that looks like in code. So what we'll do is within our over function, so partition by goes inside of the over function within those parentheses, we'll type partition by, and we are partitioning by product ID and order quantity. So now let's run that. Okay, so we have obviously retained the row-level detail of our query output, unlike with aggregate functions. But how do these groupings work exactly? Behind the scenes, SQL is creating the same groups we saw in our aggregate query based on the same unique combinations of the fields we listed in our partition by, in this case, product ID and order quantity. Then, SQL assigns each row of our data to one of these groups, returning the associated aggregate total. Now let's take, for example, the combination of product ID 707 and order quantity 24 and compare what we see in our two queries. So to do that, I'm going to run both of our queries simultaneously. So I'll just highlight both queries. and run them. Now in our aggregate query, this combination gets exactly one row in our output, as do all other combinations. And you can see that the aggregate line total for all orders with product ID 707 and order quantity 24 is 743. But in our window function example, every row in our query output with this combination of values is simply considered a member of the same group. And you can see in this case it's two records. But both records that have product ID 707 and order quantity 24 are assigned this number, 743 point a lot of decimal places, that is the exact same number as the total for those two for that product ID and that order quantity that was returned by our aggregate query. So the window function is basically returning the sum of line total for each of these rows as our aggregate function did for the entire group. So in this way, we are able to perform aggregate calculations on groups within our data without losing any row-level detail or the flexibility to include any columns we want. And if we want to add more layers to our groups, it's as easy as tacking on an extra field onto our partition by clause. But unlike traditional aggregate functions, we don't have to worry about adding or removing fields from our select or group by statements. It just works without affecting the rest of our query output in any way. So now that we've learned how to leverage window functions as a more flexible alternative to traditional aggregate functions, it's time to dig into some entirely new things they allow us to accomplish that no other SQL technique can. We'll kick that off in the next video. I'll see you then. Welcome back. Up to this point, we've basically used window functions as a more sophisticated alternative to traditional aggregate queries. And while aggregate calculations like sum or count are a perfectly good application of window functions, they also give us something entirely new: the ability to assign a ranking, either within partition groups or overall throughout our query output, to the records within our dataset. Let's go back to our sales order detail dataset for an example of what this can look like. So here we have a query against our sales order detail data, with a window function giving us the sum of line totals for each sales order ID. As you remember from the last video, each record in the dataset is assigned a group based on the field we have listed in our partition by clause, and that's sales order ID right here, and then the sum for the group, which we can also see in this aggregate query down here, is assigned to that record. So at this point, we're hopefully pretty confident in our ability to assign the individual records in our data to various groups behind the scenes and then return an associated aggregate total to each record. But what if we instead wanted to somehow rank the records within each group? For example, we could assign a ranking to the records within each cluster of identical sales order IDs, instead of simply returning a sum of the line totals for that particular ID. So what would this look like in code? The most straightforward way to implement this kind of ranking is the row number function, which we use alongside the over function in the same way we used aggregate functions like sum and count previously. Row number will assign a unique ranking beginning with 1 to every record within a group. Our groups are defined by unique combinations of values from all the fields listed in the partition by clause, just like before, assuming we have a partition by at all. So let's try that here and see what happens. So we'll start out basically by just mimicking what we've already done to calculate product line ID total by sales order ID. And we'll just change the name of the field to ranking. And instead of doing a sum of line total, we'll just do the function row underscore number and then an open and closed parentheses without any arguments passed. It's still a function, so you need those parentheses, but you don't pass any arguments to row number. Finally, we'll get rid of this comma and run the query and see what happens. Yikes! an error. So Management Studio is telling us we need to have an over clause with order by. So what the heck does that mean? Well, if you think about it, it kind of makes sense. We're asking SQL to rank records within a group, but we're not telling it how to rank them. And that's where order by comes in. So as you've seen, we already use order by to sort the data in our overall query output. But it turns out it can also be used to sort data within our partition groups to determine how records within those groups will be ranked. So in this example, let's try sorting the records within our partition groups by line amount. So syntax-wise, how that looks is that we'll take our line amount field here, and within our over function, but after partition by, we'll type order by, and then we'll drop in that line total. Now note here, there are no commas separating partition by and order by. This is a little confusing to most people who are first learning these functions. You're kind of used to arguments within a function being separated by commas, but in this case, within over, your partition by piece and your order by piece are not separated by commas. It's just a space. And if you were to be partitioning by more than one field, those fields would need to be separated by commas, but then you would not have a comma like this after the last field. There is no comma between the last field in partition by and then the order by keyword. And likewise, if you ordered by more than one field, you would have commas in between those fields after order by. So let's run this and see how that changes our output. All right, now we're talking. Our code ran successfully, and we appear to have an actual rank right here in our ranking field. But what does the rank mean? So I've gone ahead and sorted our query output by sales order ID just to clarify how this works. And please note that sorting in your overall query is not in any way necessary for a window function like row number to work. It works regardless of whether you sort your overall query output with order by, but in this case it's just useful to group the like sales order IDs so we can see how the rankings within that group over here work. So basically, within each group of like sales order IDs, so we could start, for example, with 43659, the ranking is determined by the amount of the line total, right here. The lowest total gets ranked number 1, that's $10 here, and you can see that is in fact the lowest total among all the identical sales order IDs over here in the first column. The second lowest gets ranked number 2, and so on. Now this is because we have the order by within our over function sorting in ascending order. If you recall, order by sorts in ascending order by default, so ascending order will put the smallest number first. So because the smallest number is sorted first, the smallest line total gets the first ranking. So you might have figured out by now that if we reverse the order of the sort by adding the DESC, that is to say descending, keyword after order by, right here, we get exactly the opposite result, with the highest line total being ranked number 1 instead of the lowest. So let's see what that looks like in code and how it impacts our query output. So I'll add the descending keyword after order by within our over function, and then we'll run this. And now you can see that within that group of identical sales order IDs, that first group of identical sales order IDs in our first column, that the highest line total within that group gets the number 1 ranking. The second highest line total gets the number 2 ranking, and so on and so on. And keep in mind, you can continue adding fields to your order by to sort in a more precise and specific way if you need to, just as when we use order by to sort our overall query output. Just like you can sort your overall query output by as many things as you want, some ascending, some descending, you can do the exact same thing. You have that same flexibility with order by within your over function. It's also possible to rank our data using row number without applying any groupings to our data at all. So let's see what happens if we tweak our last example by removing the partition by clause altogether. So we'll just cut out our partition by sales order ID. And then to make it clearer how that's affecting our ranking field over here, I'm actually going to sort by the ranking field. So that's the 5th column in our query output. So I'll just order by that 5th column. And then let's run that. As you can see, row number now treats our entire query output as one giant group, in which the record with the highest line total, this guy right here, is ranked number 1. And then if we scroll all the way to the bottom of our query output, the record with the lowest line total has the same rank. If we widen this out over here, has the same rank as the overall number of records in the dataset. But if we look carefully at the very end of our query output, we see something a bit odd. There are a number of records, quite a few actually, with the exact same line amount, which are nonetheless being assigned different ranks. So it turns out that row number uses brute force to deal with these kinds of ties. Row number always returns a sequential series of rankings. That is to say, row number's rankings will proceed in a 1, 2, 3 fashion, even if the values 1, 2, and 3 in our order by field are identical. There's no practical reason behind how this tiebreaker occurs. For all intents and purposes, it will randomly assign a rank to records whose values in that order by field we specified, so in this case, the line total, are identical. But what if we want to be more surgical in how our rankings handle ties? Well, that's where the rank and dense rank functions come in. We'll dive into these in the next video. I'll see you then. Welcome back. When we left off, we had identified a potential issue with how row number handles ties when ranking records within a partition group. I say potential because sometimes row number may be giving us exactly what we want, a sequence in which every record within a given partition group has a unique sequential rank. For example, we can confidently expect only one record to be assigned a rank of 2, even if several other records have the same value in the field or fields we are ordering by to determine the ranking. But there may be other situations in which we want to treat a tie as, well, a tie. And that's where rank and dense rank come into play. Let's start by taking a look at how rank handles the ties in an example similar to the one we saw at the end of the last video. So we'll start off by adding a new field to our query called ranking with rank that will work almost identically to our current ranking field, but instead of using row number, we're going to use the rank function. So first, I'll change the name of the field, and then I'm simply going to swap out row number for rank. So let's run this and see how it changes our output. So if you look at our 3rd, 4th, and 5th rows in our query, and in particular the last 3 columns of those rows, you'll see how ranking works differently between row number and rank. So our ranking column here uses row number, and you can see that even though the line total value for these 3 records is the same, the row number function is still giving us a different rank. It's maintaining that sequential order. It's guaranteeing that you're never going to have 2 records with a rank of 3. However, if we go over to our last column, which we derived with the rank function, you'll see that all 3 of these records within this particular partition group for sales order ID 43659 have the same rank, a rank of number 3. And that's because they all 3 have the same line total. And now that we get down to the 6th record and a different line total, now that ranking jumps from 3 to 6. Why is that? Because the rank function essentially skips the sequence ahead based on however many ties there are. So the next number in the sequence is reflective of that record's overall position in the partition group. So after a string of ties like these, that very next rank should be the same number as that record's position within this overall partition group. So in other words, it's going to be the 6th overall record in the partition group for this particular sales order ID. And you can see that repeating again, even with the group of records ranked 6. You have 2 identical line totals, and you see that they're both given a rank of 6, but then the sequence skips ahead to 8. Meanwhile, with row number, you've been chugging along with that ranking incrementing by 1 with every single record. Now, if you don't want these breaks in the sequence of rankings, but you still want ties to be explicitly identified, then dense rank should be your function of choice. So let's take a look at that in code. So I'm going to add another field to my query, very, very similar to the last one we added, but this one is going to use dense rank. So I'll call it, predictably enough, ranking with dense rank. And instead of using the rank function, I'll use the dense rank function. Otherwise, everything is set up exactly identically. So let's highlight that. Wait, identically? Is that a word? I'll figure that out and get back to you. So let's run this query. So now if we look again at this first partition group for this first sales order ID and compare and contrast our last 3 columns, our last 3 approaches to ranking, you should see the difference between how dense rank works and how just plain old rank works. In particular, look at the difference between these 2 rows, rows 5 and 6. With rank, because there were 3 consecutive ties, all ranked number 3, that 6th record is ranked 6th, because that's the 6th overall record within that partition group. However, with dense rank, it insists on maintaining that sequential order, kind of like row number, but unlike row number, it does allow for ties. It does allow for multiple records to have the same rank. But that very next record is going to be the next integer up from that previous rank. So even though this is the 6th record in the partition group, it only gets a rank of 4 with dense rank because it is the 4th highest line total within that group. So at the end of the day, basically row number gives you a straight sequential order regardless of ties. Rank gives you visibility into ties, but it skips gaps in that sequence of ranks when there are ties. And then dense rank kind of does something in between. It maintains that sequence so that there's no gaps in the numbers, but it still allows you to see ties within the ranks. So all of this begs the question, which of row number, rank, and dense rank should we use and when? The answer, and I really hate to sound like a politician here, is that it depends. Now, from my experience, the brute force ranking approach of row number is sufficient or really even preferable most of the time. Very often, we are trying to pick exactly 1 record from each partition group, either the first or the last typically, meaning row numbers guarantee that only 1 record will be given a rank of 1 is ideal. Rank and dense rank can also be the right tools in rarer, more specialized cases. It all really depends on what exactly you're trying to get out of your data. But they're good tricks to have in your bag, as the kids say, just in case. Now, speaking of tricks, up next we're going to change gears slightly with a couple of window functions that let you time travel, so to speak, within your data. No black holes or DeLoreans required. I'll see you then. Welcome back. I know that I mentioned something in the last video about time traveling, and I'm afraid I may have overpromised, but only slightly. We are going to learn how to use a pair of window functions, lead and lag, which let us grab values from subsequent or previous records relative to the position of the current record in our data. This is extremely useful anytime we want to compare a value in a given column to the next or previous value in the same column, but side by side in the same row. And I can tell you, in the real world, this type of comparison is done all the time. So without further ado, let's see how all this works on live data. We'll start off with this basic query against the sales order header table, which has one row for each customer order. And let's just run this to see what it returns and familiarize ourselves with the data. So we'll begin our kind of time-traveling adventure by adding a new derived column with the next total amount due value. Since this is time traveling into the future, so to speak, we'll use the lead function. You might have guessed lag would be time traveling into the past. So lead has a similar basic structure to other window functions, with the function itself being followed by the usual over clause, as we'll see here. However, it requires us to feed it several pieces of information before it will do what we want. First, we have to tell lead exactly what we mean when we say next. Our concept of next will typically be based on the sorted order of some numerical or datetime field, or maybe a sequential ID which represents the chronological order in which records were created. So our scenario with the sales order header data here actually fits the latter of these options best. So we'll use the values in the sales order ID column to determine the official ordering of our records. And we'll specify this in the order by clause of over, much as we did with ranking functions like row number previously. So now we'll just say order by sales order ID. Next, the lead function itself commonly takes two arguments. The first is the actual value we want to grab from a subsequent or previous row. In this case, we're looking for the next total due, so what we'd plug into the lead function would be total due. We also need to specify how many records we want to jump into the future, or past if we were using lag. Since we just want the next value for now, we'll stick with 1. Alright, now that we've got our lead function put together, let's see what the output of this query looks like. Alright, so the cool thing about seeing the total due column and the next total due column that we just derived lead side by side is, it makes it pretty intuitive to see just how lead is working. So if you look at our total due amount in the second row, this guy right here, 1457, you can connect that to the next total due amount that we derived with lead in the first record. So what that means is our lead function allowed us to essentially grab the next value in this column and place it side by side in the same row. So now if we wanted to, we could do comparisons with functions in the same row of data between the current total due and the next total due. You can imagine how useful this might be with time series reporting, where you want to compare the current value versus perhaps the next day's value or the next transaction and get some kind of a difference between those two. So, and you can see the pattern continues all the way down. The next total due on a given row is always the total due on the very next row. And we define next in this case again by the ordering of sales order ID. So now that we can use lead as our crystal ball to peer into the future, what about the past? That is to say, how do we go about grabbing the previous value in a field as opposed to the next value? The answer is the lag function, and it's dead simple to use once you've got the hang of lead. So simple, in fact, you can literally swap the functions, leaving all the other arguments unchanged, and it will do exactly what we want. So all I'll have to do here to get our previous total due item working is to copy this lead function we've already written and just replace lead with lag. Now we'll run that. And if you look at the data, you'll see it is in fact doing the exact opposite of what our lead function was doing. So the total due amount in our very first row was roughly 23,000, And then if we look at the previous total due that we're generating with lag in the second row, it's that amount. So the previous amount relative to this second row, the previous total due in the second row would have been 23,000, and that's exactly what our lag returned. You might notice that we have a null value for the very first record. That's because there is no previous value of total due relative to this first row. So one question you may be asking at this point: can we sort the field in over's order by clause in descending order for lead and lag? And if so, how does this affect our output? The answer is you can, but you usually shouldn't. You probably shouldn't. In a chronological or time-based sort like we're using here, which from my experience is the most common scenario in which lead and lag are used, the default ascending sort means that smaller or older values, because that's essentially the same thing, that's the way SQL looks at time values, an older value is a smaller value, are considered lower in the sort order, while larger or later values are considered higher. Now, since lead looks forward and lag looks backward, both functions work naturally if you just use the default ascending sort order on the field in order by. If you apply a descending sort, on the other hand, you can still grab either the next or previous values, but you'll have to use the opposite function from the one you'd expect. Lead will now return previous values, while lag will return next values. To me, that's pretty confusing, so I just suggest using the default sort order so lead and lag can be deployed in situations where they most obviously make sense. Just make it easier on yourself. As long as you stick to that default ascending sort order, the use of lead and lag will simply just make more sense to you. But I digress. So let's go back to our previous example and see what happens if we play around with that second parameter of lead and lag, the one here that's saying we want to jump one row into the future or one row into the past. Let's change that to a 2 and see what happens. And we'll run that. Now, if you look at the next total due value in our first row and think about what we're really trying to do with the lead function here, we're saying I want to see not the next value in the column for total due, I want to see the second value away, the second value offset from my current row. So what I would expect is if I looked down in the total due column, not one row, but 2 rows, I should find a value that matches what I'm seeing in my next total due column. And that's exactly what's happening. Likewise, if I go to my previous total due column in the 3rd row, I know that I'm looking back 2 rows from this row. So if I look back to my total due column 2 rows from this row, I should get the same number. And sure enough, I do. So now that you're an expert on window functions, you may be wondering where partition by fits into all of this. The answer is pretty much the same way as with all the other window functions we've covered. I've omitted the partition by in our examples up to this point so we could focus more on the mechanics of lead and lag. This means the entire dataset was essentially being treated as one giant partition group in which the next value was always the next value in the overall query output. As before, adding partition by will simply slice our dataset into virtual groups based on the unique combinations of values in whatever fields we list after partition by. Our next and previous values will then be defined within those groups rather than across the entire dataset. So if we partition the window functions in our previous example by, for example, customer ID, the next value will come from the next record that has the same customer ID. So let's tack that onto our code example and see how it works in action. All right, so the first step will be to partition by customer ID in our lead and lag functions respectively. So we'll go ahead and add partition by to our over, and remember that goes before the order by. If I can actually spell and type partition by. And then since the last part of these two functions is identical, we'll just copy paste down to our lag. And To simplify the output and just focus more on how the partitioning is working within lead and lag, I'm going to make the second argument of both lead and lag just one, so we're only looking forward or backward one record. And then the last thing I'll do is sort the overall query output by customer ID in addition to sales order ID. Now this isn't necessary for lead and lag to work, it's not changing how they work in any way, but it should help clarify how lead and lag are working within the partition groups, within those groups of like customer IDs that we're creating with the partition by. So let's run this. All right, so now we're partitioning by customer ID. So instead of looking at things across the entire data set, we really need to look in terms of groups of records, records that are grouped by the unique values in whatever field we specified in partition by. We specified customer ID, so we need to look at these functions as operating over these little groups, these windows of our data. So we've got 3 records with customer ID 11,000. So we'll look at those just as kind of like its own independent data set. So we have a total due of 3756 in our first record. So what I would think is, if I look over to my previous total due amount in the second record, it should match that. Because if I'm in the second record and my amount in this previous total due field is a certain number, then if I go back one record, if I go back in time one record to look at what that total due amount was in the first record, it should be the same. Likewise, if I look at my next total due amount in the first record and then cross-reference that against my total due amount in the second record, those two should match again, and they do. And if you look down at the other windows, the other groups of related records, the same pattern emerges. The next total due amount in the first record in the group will match the amount in the sort of base field, the regular total due field in the second record. The amount in the previous total due field will equal the regular total due amount value in the previous record. Alright, so that about does it for lead and lag. I know these functions can be a little tough to wrap your head around at first. They certainly were for me. But trust me, it's well worth it to master them. Knowledge of window functions in general, and lead and lag in particular, will really help you stand out as an analyst and a SQL coder. They are not only extremely powerful techniques, but also not as widely understood as you might think. I know plenty of analysts with years and years of experience who still don't have a strong understanding of lead and lag, and end up using all sorts of cumbersome hacks to do the same things lead and lag can accomplish in a single line of code. The bottom line is this: if you don't feel like you're really solid on the content, try rewatching the video and playing around with the code examples. You'll thank me when you're coding circles around your teammates. Okay, that's enough preaching for me. I'll see you in the next video. Welcome back. Thus far, all the queries we've written have consisted of a single step, a single select query. But in the real world, complicated data analysis often requires multiple, and sometimes many, steps. For those situations, we need some way to break these problems into smaller, more manageable pieces. Now, there are actually several techniques for doing this in SQL, all of which have their place, but we'll start by looking at the simplest type, which is subqueries. As a motivating example, let's take a look at one of the queries we created earlier on when we covered the row number function. If you recall, this query ranks the items within each sales order by their line total. But what if we weren't interested in seeing all the records in the table, but rather the single record with the highest line total per each order? How could we accomplish this in SQL? The most obvious approach is to take the window function from our select and simply drop it into the where clause, where we can apply our criteria. So let's try that and see what happens. So I'll just copy our window function right out of the select and add a where clause, and we'll just try to set this equal to 1. Basically, the goal is to pluck this record and so on and so forth out of our data. we're basically trying to identify out of each group of like sales order IDs, we only want to see the one record that had the highest line total. So let's run this and see what happens. Ouch! So SQL is now giving us an error message. We're apparently only allowed to use window functions in the select and order by clauses, which leaves where out. So how the heck are we supposed to apply criteria to the fields that we generate with our window functions? The most straightforward answer is subqueries. Subqueries work pretty much like they sound. There is an inner or subquery that is nested within and then referred to by an outer query. We are essentially defining a kind of virtual table in one select query and then referring to that table in our outer query as though it was any other table in our database. But enough talk about subqueries. Let's take a look at how we can apply them to solve our problem here. The first step should typically be to build and test the query that we will need to refer to as a table later. This initial query will ultimately be our subquery. In our case, we've already written the subquery, which is our query with the window function right here. Now we need to be able to refer to the output of this query as though it is, again, simply another table in our database, so we can apply criteria to this ranking field here that we created. The syntax for doing all this is pretty straightforward. First, we'll simply wrap our entire subquery in parentheses. So I'll start by entering down one and adding an open parenthesis before, and then a closing parenthesis after our inner query. And note that I'm not going to be keeping this where clause from our original query because, and you will see this more in a later step, I'll be applying the logic from our where clause in the outer query. So we'll get rid of that. But before we write any more code, I want you to try and visualize this query wrapped in parentheses that we see here as simply a reference to a table in our database, except the table, as it were, is just the output of the query. So if I run this query, just as a visual aid, try to imagine that this query output you see down here is just another table, and you can select fields from it like you can any other table, and just as importantly, if not more, you can also apply criteria to it, just like you could another table. And those criteria could include something like setting line total ranking equal to 1. Looking at subqueries this way will go a really long way towards helping you understand them, especially when you're trying to read and interpret someone else's code that makes heavy use of subqueries. But back to our code, now that we have our virtual table defined here, it's simply a matter of selecting fields from it like we would with any other table, and then applying criteria to the appropriate fields in the where clause. So let's give that a shot. First, I'll add my select up here. And just to keep things simple, I'll do a select star. And we'll also need the from keyword, just like you would with any normal query. And as I mentioned previously, I'm going to add a where clause below our subquery, below this closing parenthesis that marks the end of our inner query. And I'm going to apply that criteria we tried to use earlier to our line total ranking field by just asking SQL to return us any records where that line total ranking is equal to 1. So you probably see these little squiggly red lines here, and you probably know that means this is going to error out, but let's go ahead and run it just to make sure. And it did. So it turns out we're getting this error because we actually need to name or alias our subquery in the same way that we might alias any other table we bring into a query. So let's alias it A and try to run it again. So I'll just add that A afterwards, highlight, and run again. And there we go. Just like that, our problem is solved.
Well, folks, that's it for this video. I hope you found it useful and maybe even enjoyable. And if you did, I'd be remiss and a terrible YouTuber if I didn't politely ask you at this point to like and subscribe. You could even smash that subscribe button, as people so often seem to say, Although unless you have a backup computer, I wouldn't necessarily recommend that. Anyway, be on the lookout for more new videos most every week. I don't know exactly what they'll be about. Probably something analytics or AI adjacent, but I may stray a bit from time to time. So stay tuned and we'll find out together. Okay, I'll see you in the next one.